Hello, my name's Jack Porter. I'm the Unreal Engine mobile lead, and today I'll be talking about Unreal Engine 5 mobile rendering. I'm going to start talking about what's new in Unreal Engine 5 and 5.1 and the differences from Unreal Engine 4. And after that, my colleague Dmitriy는 will take over and discuss the deferred shading mode in some detail. The Unreal Engine 5 mobile renderer is an evolution of what's available in Unreal Engine 4. In UE4, it was mostly a forward shading renderer. We did have an experimental deferred mode. In UE5, we've enhanced this to be more of a forward plus shading renderer, and we think the deferred shading mode is approaching production ready status in 5.1. We still only support a single shadowed directional light, typically the sunlight when you're outside. We support multiple point and spotlights with optional spotlight shadows. In UE4, we didn't support shadows and we had a limit of 4 lights per object. We have per pixel reflection capture selection, which improves image-based lighting quality. We have support for more shading models, and more than the simple bilinear upscaler, we now have FSR, which is an improved upsampler. And we have more anti-aliasing modes, including the full, if you want to use it, you have the full generation 4 TAA, temporal anti-aliasing, and FXAA. There are some features of Unreal Engine 5 that do work on mobile but have limitations or differences. I'll just list a few of them here. The first is sky atmosphere. In Unreal Engine 5 on desktop, simply the background of your level automatically renders sky atmosphere and volumetric clouds. But with the mobile renderer, you need to create a static mesh sky dome like you used to in Unreal Engine 4. And at this stage, volumetric clouds are not yet supported. Runtime virtual texturing is a feature that allows you to improve performance by taking a complex material like a landscape, which has multiple layers, and as you move through the level, caching all those layers, collapsing them, and storing that data in a texture. And this does work and gives a performance improvement on mobile as well, but compressing those textures in real time is too slow for mobile GPUs. So we have to use uncompressed textures, which has a memory cost, and you need to make a performance versus memory trade-off in order to make use of runtime virtual texturing. In UE5, GPU scene is enabled by default for desktop. It's not enabled by default yet for mobile, but it does work on all devices. It provides some benefits, but it has some limitations that I'll discuss in a moment. One of the biggest enhancements to quality that we've made is the forward plus renderer, and as I mentioned, we're no longer limited to 4 local lights per object. These are still rendered as part of the base forward pass, but we have brought the light grid, it's called. It's a frustum space culling technique from the desktop forward renderer. We've brought that to mobile, and this allows us to cull the lights and work out which lights are affecting which regions of the screen independently of individual objects. And so this makes many lights and reflection captures available to each object in the pixel shader, and then the pixel shader uses the light grid to select the appropriate lights and reflection captures independently for each pixel. The 2 checkboxes there under rendering settings enable the local lights and the clustered reflections for mobile forward. So in this scene, the floor is a single static mesh, and without forward plus, a single reflection capture is used for the entire surface. And because this floor extends outside of this location here, only a single reflection capture has been chosen. And in fact, you can see there's a big, looks like a reflection of a window on the floor. It doesn't represent this scene at all. That's representing somewhere way out of this area of the level. But because we can only choose a single reflection capture per object, unfortunately, that's the reflection capture that's been chosen. But with forward plus, we can choose the best reflection capture per pixel. And in this case, you can see the reflections of the lights on the ceiling being reflected quite realistically. The result is very similar to the desktop renderers. We do have a deferred mode, as I mentioned, and 5.1 has brought this to close to production-ready quality. It's designed to take advantage of the tiled mobile GPUs, and that's a feature of mobile GPUs that stores or allows a tile of the screen to be stored in some very fast memory. And we make use of this memory to increase performance. It also adds a number of lighting features that are not feasible with a forward renderer at all. And Dmitry is going to provide some more details in the second half of this session. So which rendering mode should you choose for your game? First of all, if you're using, or if you're targeting a GPU that doesn't have the tiled, that is not a tiled mobile GPU, then it doesn't make very much sense to use mobile deferred. It won't be any faster. And so for Nintendo Switch, we use mobile forward. If your game uses pre-computed lighting and shadowing, then it's also probably going to be best to use mobile forward. The extra data required for the lighting causes problems with mobile deferred, and there are more limitations that introduces. And the dynamic lighting features that become available are no longer relevant if you're using pre-computed lighting and shadowing. Forward Plus is beneficial if you do have local lights or many reflection captures, such as that scene I showed previously. The mobile deferred mode, as I said, takes advantage of the tiled mobile GPUs. Best if you used dynamic lighting or want to use some of the extra lighting features that it supports. GPU scene is a feature in Unreal Engine to provide auto-instancing. It's been technically supported since 4.25, but we've improved it for UE5 by adding some per-instance culling on the GPU. This improves performance and also solves some limitations that some mobile devices had that were preventing it from being used in UE4. It's still not a clear win in all cases, but if you've designed your content with instancing in mind, then it can be beneficial. It is disabled by default on mobile. You should try it out and see if it makes your game faster or not. It does have some limitations. The light map and the shadow map texture have to be the same. The base requirement is that the material instance and the mesh are the same. But as well as that, the light map and the shadow map texture have to be the same, as well as the reflection captures. For these reasons, meshes that are placed nearby each other instance the best. If the material uses some of this per instance data inside its vertex shader, then batching will also not be possible for that particular instance. And the material property, the material nodes such as the actor location or the object bounds or the object position, all of those require data that is going to be different for each instance, and therefore batching might not be or will not be possible. That would occur if you were to attach some of these nodes to, for example, world position offset, which generates vertex shader code. You may know that r.screen percentage is a console variable that allows you to render the 3D scene at a lower resolution from the rest of the UI. At the end of the 3D scene, we upscale it, but before Unreal Engine 5.1, that was only using a simple blurry bilinear filtering. 5.1 adds something called FSR, which is AMD's Fidelity FX Super Resolution. And this is a post-processing filter with two passes, the first of which does upsampling, taking edges into account, and the second of which is a sharpening pass called CAS. We use a mobile-specific version of this, which has half-precision math to increase performance. And on a mid to low tier device these days, such as a Pixel 4, it takes around 1 millisecond for the upsampling pass and around 1.5 for the sharpening pass. Using FSR should allow you to use a resolution that saves a fair more than that 1.5 milliseconds overall, and so your overall GPU time is reduced with a similar quality to what you'd have if you hadn't used screen percentage at all. So here are 3 screenshots, the first of which is the original 100% resolution, and this took the GPU 24 milliseconds to render this scene. Just with the upscaling pass, you can see it's still quite blurry, but we've saved 6 milliseconds overall. If we spend just 1 more millisecond, then we can run the sharpening pass, and both, but that end result is quite similar to the 100% resolution. And so overall, you've saved more than saved around 5 milliseconds. And so for your low-end devices, if you enable FSR, you can reduce your overall GPU workload by rendering the scene at a lower resolution, but still having some similar quality to what you'd have if you hadn't reduced the resolution. We've made some improvements to mobile preview in the editor. There are you have the ability to set different rendering settings for different platforms. For example, Nintendo Switch, you could enable distance field shadows where they perform quite well, but for Android, you might not want to enable those. But previously, the editor used a single shader platform for all of the platforms you're previewing, and that prevented us from having per platform settings. This issue has now been solved by having independent shader platforms for each of the platforms you want to preview, and so all of them can have different rendering features enabled or disabled, and you can preview that correctly. Because these are independent, the shaders can be cached correctly in the derived data cache, and this means the time to change preview platforms between iOS and Android and Switch, and then back to desktop, that can be, or that is reduced. And if the data is in the derived data cache, then it's pretty much instant to switch. Another improvement to mobile preview is the fact that we now load the device profile and the scalability INI values for the preview session. So if you're in the editor, press or toggle mobile preview on, it will load the scalability settings from, for example, Android scalability.ini, and apply that so the LOD transitions might happen differently or compared to PC, if that's what the scalability that you've configured is set up for. This is a runtime improvement. Android, the PSO cache is a list of all of the shaders your game is going to encounter. And we gather this list so that when we start the game, for example, on Android, when you start up Android on first launch, we will load and compile all of those PSOs to ensure that there are no hitches in gameplay. And previously, we tried to make this happen in parallel. You've got a number of CPU cores that should, in theory, be able to compile multiple PSOs simultaneously. But we found that Android GPU drivers either didn't handle as well, they would crash or be unreliable, or we had issues where the drivers were, in fact, preventing any parallel operation from occurring, and so we're not getting any speed up. 5.1 sidesteps this issue by using a separate Android worker process for both Vulkan and OpenGLES, and this allows us to spin up one process for each CPU core we want to use. So if you want to allocate 4 CPU cores, the optimizing and pre-compilation of your shaders will occur 4 times faster than it would. There are also some miscellaneous Unreal Engine 5 optimizations we've made. The skin cache is now supported on mobile. This caches the final skinned vertex locations at the start of the frame and reuses them for the subsequent render passes. This can provide a benefit depending on the features you've enabled. Fog is now rendered as a separate pass. This does save a little bit of CPU time, but the bigger saving is the fact that we're removing all of the fog code that used to be applied to the end of all of the materials, the shaders generated from the materials. By removing that by that duplicated fog code and sharing it in the single render pass that's being done separately, That saves a fair amount of memory and package size. The amount that's saved will depend on the amount of shaders you have in your game, though. But for us, it was quite a benefit. We've also removed the mobile-specific landscape rendering, which used to use a mesh, and we now use the landscape height field, the same as the desktop path. This saves some memory. The mobile-specific path is no longer required because some very old OpenGL devices that are no longer supported were the devices that required that particular layout. So that's a memory saving and also a slight performance boost. We now ship with Vulkan enabled. Vulkan does perform better than OpenGL ES, and we have some device profile rules. If you're running one of those GPUs listed there with the Android version listed, Unreal Engine will now automatically choose Vulkan for that device. Fortnite Android, we use more restrictive rules than this. And we found that games with very complex content pretty much are going to require some testing of Vulkan to ensure there are no driver compatibility issues. And that's actually the reason why we've limited certain GPUs to certain Android versions. All but the very latest versions of Android have required, a little bit of testing for us to make sure that the drivers are on those older versions of Android are reliable enough to enable Vulkan for the Fortnite content. If you have a complex game, I would recommend doing some testing to ensure that there are no compatibility issues with your game in Vulkan mode. We've also transitioned our shader pipeline. We now use something called DXC to compile our shaders for all platforms. We were using this previously for iOS, and we've now transitioned to Android as well. And this was the reason why half precision didn't work for iOS in the last couple of Unreal Engine 4 versions. I know a lot of users had requested that we add back half precision support, and we've done so for DXC in version 5.1. We now support the use of both real and emulator uniform buffers, which is good for performance. And one thing we found when we implemented DXC was the Vulkan drivers, especially on some early Adreno drivers, were not reliable. We've added some workarounds for this and performed some extensive testing to ensure that this transition is smooth. Now, one of the great Unreal Engine 5 features for high-end PCs and for next-generation consoles is Nanite, and its ability to remove the draw call count and polygon budget concerns so that content creators no longer need to be worried about this at all. And similarly, Lumen allows you to light your level pretty naturally, just placing a sunlight and maybe a few lights here and there, and then having the global illumination system bounce and light your entire level quite naturally. Unfortunately, current mobile devices don't have the hardware features or the required performance to enable Nanite and Lumen. Nanite will use the fallback meshes, and these are regular static meshes that get rendered in place of the Nanite meshes. But your scenes, because they're regular static meshes, your scenes will need to look at the LOD and hierarchical LOD setup to make sure the draw call counts and polygons are under control. Because Lumen global illumination is not supported, scenes will also need to be manually lit. You could use a lighting scenario if you wanted to use Lumen on high-end PC and next generation console, but mobile would continue to be lit in the traditional way. Nanite requires the 64-bit atomic instructions when it generates its visibility buffer. There is no mobile GPU at the moment that has this support. We're hopeful that future mobile GPUs will support it though. And mobile hardware that supports the standard space ray tracing is becoming available. And theoretically, this should be able to support Lumen's ray tracing pipeline. For example, the Xclipse GPU in the Galaxy S22. Upcoming Android GPUs such as ARM's Immortalis GPU also have this support. So we're currently investigating the Lumen ray tracing pipeline on Android hardware using Vulkan. We don't expect it to perform very well on current devices, but as mobile GPUs continue to advance, eventually they will be able to run these ray tracing shaders enough to enable Lumen as being a practical way to light your levels on this hardware. I'm now going to pass the session on to Dmitriy는, where he's going to detail the deferred shading in Unreal Engine on mobile.
Hello, my name is Dmitriy는, and I work as an engine programmer for Epic Games. And today I will talk about deferred shading on mobile. I will dive into more details about how it works, what kind of limitations it has, and what you can expect from it. We have been experimenting with deferred shading on mobile for some time. A first working version was added in Unreal Engine 4.26. It was a bare-bone version with a lot of features missing in it. I want to make clear this is not a port of desktop deferred render to mobile. This is a new mode in existing mobile renderers that can exploit tile-based GPUs to do the deferred shading. In Unreal Engine 5.1, we will be making mobile deferred shading as an officially supported feature. It will support all mobile platforms, which include iOS, Android, both Vulkan and GL, and also Switch, Nintendo Switch. Recently, we have been testing this rendering mode in Fortnite Mobile, and it shows promising results, improving overall performance, reducing memory usage, and number of hitches during gameplay. Along with performance, it adds some new rendering improvements that were missing in default in a default mobile forward renderer. Option to enable mobile deferred shading can be found in the project settings in mobile section of Unreal Engine 5.1. For an older Unreal Engine versions, you will have to add the r.mobile.shading path equal 1 into your project default engine.ini. Quick recap on what the difference is between forward and deferred shading. With forward shading, we compute material interaction with lights and shadows at object draw time and write the shaded pixels into the frame buffer. So that means our material shaders has to include all the light and shadow code. With deferred shading, we split problem into two passes. The first pass, usually called geometry pass, we store required material attributes like base color, roughness, metalness, and some others into a temporary buffer, usually called G buffer. Then we run a second pass, it's called usually lighting pass, which reads material attributes from a G buffer, computes lighting for it, and writes shaded pixel into the frame buffer. Both shading methods has some pros and cons. Deferred shading allows you a more efficient implementation of some lighting features, which I will talk about next. But at the same time, it has some disadvantages. Like MSA, multi-sample anti-aliasing, is not really feasible with deferred shading because MSA requires additional storage in the G buffer, and it has much more expensive lighting path, where you have to shade each sample instead of each pixel. About the exclusive features you get with mobile deferred shading compared to forward. First is the light functions, which allow you to assign a material to a light and which will filter the light bright intensity. I should mention that it works only with non-static lights, so it is fine for movable and stationary lights. Second is light profiles. It's a special texture you can assign to a light that will define its brightness. Also, you will get the properly lit decals. For comparison, mobile forward supports only emissive, which are unlit decals. However, there are a few limitations with decal rendering, which I will explain on the next slide. You also get an efficient rendering of local lights. Since lighting is separate from materials, using local lights does not need separate shader permutations. lights can be rendered one by one as a geometry with depth and stencil culling. We use the sphere shapes for the point lights and cone shapes for the spotlights. And we use the full screen quads when we render the global directional lights. There is also an option to use the clustered rendering where we can apply all lights in a single draw using a light grid structure. This can be beneficial only when you have around 100 slides or even more. Decal rendering limitations. Lead decals are not supported with static lights. To properly support them, we will have to use a dbuffer. Dbuffer is a special gbuffer-like storage exclusive for decals. And to use dbuffer, you will have to force a use of depth prepass. And also you will have to reserve 3 additional samplers in a base path shaders to read the dbuffer textures. This is fine on desktop rendering, but it's not feasible for mobile rendering. Emissive decals work fine with static lights. There is another limitation with decals in mobile deferred renderer. Because of certain limitations on gbuffer size, which I will explain a bit later, we have to use octahedron encoding for normals to reduce their storage requirements. And these encoded normals cannot be blended. So if your decal tries to modify normals in gbuffer, it will not really work on mobile. But fully overwriting normals is fine. Along with visual improvements, the first shading has another benefit that can reduce memory usage and reduce shader compilation hitches. With the first shading, all lighting is separate from materials. Let's take a look at basic materials that uses most common default lead shading model. It does not use any textures and just provides a constant values for material inputs. With forward shading, this material will use around 147 instructions and 2 texture samplers. So one sampler for shadow map and 1 sampler for reflection texture. With the first shading, instruction count for the exactly same material goes down to 34. These instructions are spent on encoding material attributes into the gbuffer. This is all what this material does. It does not use any samplers for shadow map and reflection, since shadows and reflections will be applied later in a lighting path. This is another benefit of deferred shading. There is actually more free samplers available to artists out of total limit of 16 samplers. The current 16 samplers limit is dictated by Android OpenGL limitations. The first shading in general needs less shader permutation for each material. When your project does not use pre-computed lighting, opaque materials need only a single pixel shader. In forward case, depending on project settings, material needs around 3 permutations on average. As an example, here is a comparison for the shader library from Fortnite Mobile on Vulkan. Library for deferred shading is about 7.5 megabytes smaller. It's around only 3% reduction. Doesn't seem like a big win, but I should mention that Fortnite Mobile has already been optimized to reduce shader permutation as much as possible. There is often just a single permutation for materials even in forward case. And duplicated lighting code in all materials compresses very well. Also, deferred shading reduces size only for pixel shaders, and vertex shaders stay the same. Depending on content, you can see a bigger wins than Fortnite in shader library size reductions. And the deferred shading will always reduce size of the shader code. It's just the percentage that may vary. Here we can see a performance comparison that was captured when testing deferred shading in Fortnite. We tested performance on the devices with two of most common Android GPUs, which is Qualcomm Adreno and ARM Mali. I should say that for this test, we were running a 7-minute replay file, looping it 3 times. So in total, it was around 20 minutes of continuous gameplay. Usually, first loop is quite hitchy as we compile the new encountered pipeline state objects. We compile them on the fly. And second and third loops are more smoother since all the pipeline state objects already cached. These numbers are an average of that 3 loops. We can see that the third option performs better on both devices. It has better MVP. MVP is a missed vertical sync percentage. So you want this number to be as close to 0 as possible. It has less hitches, mostly because smaller and simpler shaders take less time to compile on the device. And you get better performance on the CPU. The third shading requires much less graphic state, and we just need to do less work on the RHI thread. When you do less work on the RHI thread, that frees up the big cores on the device for other threads, so they will take less overall time because of the less contention. Mali devices also see a reduced memory usage because they support a true memoryless render targets. The Adreno shows a slight memory regression. It seems like Adreno 640 does not really support memoryless targets, so it actually allocates system memory for gbuffer. Some of the implementation details. The third shading is implemented with tile-based GPUs in mind. Tile-based GPUs are the most commonly used GPUs on mobile devices. They are quite efficient for battery, and as they don't require a lot of memory traffic between GPU and system memory, if you use them properly. GPU buffer exists only in tile memory inside GPU and is never read or stored to a system memory. gbuffer also does not have any memory allocated when device supports lazily allocated memory type. Since gbuffer does not exist in memory, it cannot be sampled as a texture in the post-processing. For each mobile platform, there are different ways to achieve on-tile shading. On iOS, we can use the frame buffer fetch-like functionality to access gbuffer on tile. On Android Vulkan, we can use Vulkan subpasses. On Android GL, we have to use extensions. Unfortunately, there is no universal way for all GPUs. On Mali and PowerVR, we have to use the Pixel Local Storage extension. On Adreno GPUs, we have to use the frame buffer fetch extension. Switch consoles have the Nintendo Switch consoles have an immediate mode GPUs, so this on-tile techniques does not really apply to them. gbuffer is allocated as a regular textures in the system memory. Also, I should mention that we tested the third mobile render on Fortnite Switch, and it was about 1.5 milliseconds slower than forward, mostly because of increased memory traffic for storing and reading gbuffer from memory. Each method or extension we use to implement on-tile default shading has a certain limitations on different devices. On iOS, we can easily fit into limitations as even old devices like iPhone 6 allow you to use 8 color attachments with a total size of 256 bits per pixel, which is enough for mobile rendering. If we look at Android GL, on Adreno GPUs, we use the frame buffer fetching extension, and it allows you to access 8 color targets with no apparent per pixel restrictions. So we are fine here. However, on Mali GPUs, we use the Pixel Local Storage extension. And even on quite modern devices, it reports that you can use up to only 128 bits or 16 bytes per pixel. This is only for color data. Depth is accessed separately and does not count against this limit. 16 bytes is quite limiting, and I will explain a bit later what kind of implications it has on supported features. We were thinking that Android Vulkan will not have such limits like OpenGL, but unfortunately, it's not the case. Not so old Mali GPUs like the one used in Galaxy S9 report that you can use only up to 4 color attachments. So that limits our G-buffer to only 4 color targets. And there is another limitation that exists even on more modern Mali devices like Galaxy S10. To access G-buffer on tile, we have to use special input attachments. And the limitation says that you can use only up to 4 input attachments. That means we can use only 3 color attachments plus 1 depth attachment for reading in the lighting path. Because content should look and work the same on all mobile platforms, we have to use the most strict limits out of all platforms to make sure it works everywhere. To summarize all limitations, we can use only 16 bytes or 128 bits per pixel in a G-buffer. We can use up to 4 color attachments, and we can fetch only 3 color attachments plus 1 depth in a lighting path. If you want to drop this limitation in your project, for example, if you don't plan to support all Android devices, you can find this function mobile uses extended G-buffer and make it return true. So what kind of implications these limitations have? When your project uses pre-computed lighting, this is G-buffer layout we have to use to fit into all limits. This G-buffer uses 4 color targets and for 16 bytes per pixel in total. We have to use encoded normals to save 10 bits for indirect irradiance. And as I said before, this makes decal that blends normals to not work correctly. Overwriting normals is fine, so opaque decals will work correctly here. Some shading models need to store additional data into the G-buffer. For example, subsurface shading model need to store RGB subsurface color and 1 additional scalar for opacity. So 4 additional bytes. There is just no space for it with current limitations. This means shading models that require additional data are not supported by mobile deferred renderer if your project uses pre-computed lighting. If you need to support these shading models, you will have to drop support for devices with 128-bit limitation, or you have to use the forward shading instead. When project does not use the pre-computed lighting, we have more free space in our G-buffer. Here we can use some context knowledge about each shading model to fit their custom data into G-buffer. For example, for subsurface shading model, we know that metallic attribute is not used. Currently, there are only 11 shading models, so 4 bits will be enough to encode shading model ID into G-buffer. We can reduce quality for a blue channel in subsurface color, since its contribution to overall color is less important. We pack shading model ID and the blue channel into 10 bits and store it where it was indirect irradiance was. Rest of 2 color channels we store in G-buffer B and C, and we store opacity where metallic value was. Still, we have to use encoded normals so will be no correct blending for decals with normals. Also, there is no space for material ambient occlusion. When material uses a shading model with a custom data, we don't support ambient occlusion for it. But a default shading model is fine, and it will support ambient occlusion. In similar fashion, we encode all supported shading models into 128 bits. So when your project has a pre-computed lighting disabled, deferred shading will work with all supported shading models, and with some certain limitations like missing ambient occlusion. So to summarize, in Unreal Engine 5.1, we will support default lit, clear code, subsurface, pre-integrated skins, subsurface profile, two-sided foliage, close hair and eye shading models, and also single layer water, which is translucent. And also a per pixel shading model that comes from material expressions. This per pixel shading model is quite expensive because you have to use the dynamic branches, so you should use it with care on mobile. Translucency always uses forward shading and is rendered the same way on both deferred and forward shading renderer. This deferred shading is quite expensive to support multiple shading models, as your lighting path shader has to use the dynamic branching to properly shade each pixel. Pixel shader has to fetch shading model ID from the G buffer and then, depending on its value, to do one or another type of shading. Usually, most of pixels use default lit model, and sky is commonly rendered as unlit. This is a typical screenshot from a Fortnite content, where you have about a third of the all pixels using the unlit sky, and most of the rest of the pixels use the default lit shading, and only 2 cars use the clear code shading model. It will be nice to use expensive shading only for pixels that really need it. On mobile, we use a stencil to mark certain shading models. We reserve 2 bits in a stencil buffer for it. When we render material in a base path, we write 0 to stencil for unlit pixels, we write 1 for default lit pixels, and we write 2 for all other shading models. In a lighting path, we render each light 2 times. At first, we use a simple and fast shader that can shade only default lit pixels. It does not need to fetch shading model ID from G buffer and does not use any dynamic branching. Also, unlit pixels do not need any shading, so they are not processed by a lighting shader. You can see on the left picture that pixels in green they are passing the stencil test and get shaded. And on second pass, we use a general shader that can shade any shading model. We set stencil test to 2 and run it only over pixels that use shading model that is not unlit or default lit. You can see on the right picture that only 2 cars pass the stencil test, and most of the pixels are skipped. There are more improvements we can do for mobile deferred shading. For example, we can render each light only once if we detect that there are currently no visible objects that use non-default shading model. We can give access to G buffer for translucent materials. Translucent shaders can fetch G buffer the same way as lighting shader does. But you can fetch only current pixel G buffer and cannot sample any other pixels. Also, screen space reflections will be a nice feature for mobile deferred shading. Problem is that we will have to store some of the G buffer targets to a system memory where a reflection shader can sample them. That will increase memory traffic between GPU and system memory and could be expensive. And that's all for today's session, and if you have questions, we will answer them in the Q&A session. Thank you.